Suppose we want to calculate 1 minus I to the power of 100. Well, we could write out 1 minus I 100 times and do the multiplication. Another thing that we could do is use the binomial theorem. So the first term is 100C0, and we would multiply that by 1 to the power of 100 times minus I to the power of 0. But 1 to the power of anything is 1. Minus I to the power of 0 we're assuming is 1. We're assuming that the usual rules of algebra apply to complex numbers. So a complex number to the power of 0 we're assuming is 1, just like any number to the power of 0 is 1. The next term would be 100C1 times 1 to the power of 99, which is 1, times minus I to the power of 1. So we can forget about the 1 to the power of 99. 1 to the power of anything is 1. The third term would be 100C2 times minus I squared, and so on. So this is just a binomial theorem where A is 1 and B is minus I. The way we would actually do this calculation in practice is to use a famous formula from or by Abraham de Moivre, also known as de Moivre's theorem. To use de Moivre's theorem, we first of all write our complex number in polar form. So just to remind you of how you do that, we first of all plot the complex number on an Argand diagram. So the real part of this complex number is 1. The imaginary part is minus 1. That's the coefficient of I. So this point here is the number 1 minus I. We need to get the distance of it to the origin, which is called r, and we need to find theta, which is measured anti-clockwise from the positive real axis. Well, r is found by Pythagoras' theorem is the square root of the real part squared plus the imaginary part squared. The real part squared is 1 squared. The imaginary part squared is minus 1 squared, which is the same as plus 1 squared. So we get the square root of 2. Now what about theta? Well, to find theta, we could start by finding the acute angle A, which is in this right angle triangle. We see the side opposite A is 1, the side adjacent to A is also 1. So we see that tan of A is 1 divided by 1, which is 1. That means A is 45 degrees. If A is 45 degrees, it means that theta is 315 degrees. So now we can write our complex number 1 minus I as r, which is root 2, times cos theta plus I sine theta, where theta is 315 degrees. And you can always check this. If you multiply root 2 by cos 315 degrees, you should get 1. That's the real part of this complex number. If you multiply root 2 by the sine of 315 degrees, you should get minus 1, which is the imaginary part of this complex number. The sine of 315 degrees is actually negative, because for an angle in this quadrant, only cos is positive. Only the cos of an angle in this quadrant is positive. This comes from the cast rule, CAST. So everything connects back to trigonometry. This is the C quadrant, where only the cos function is positive. Now, after writing 1 minus I in polar form, then we raise 1 minus I to the power of 100. So we raise all of this thing here to the power of 100. And this is where de Moivre's theorem comes into play. We have a product in here. We have root 2 times this complex number. When we have a product raised to a power, we just put each part of the product to the power. So we put root 2 to the power of 100, and we put all of this here to the power of 100. Now, de Moivre's theorem says that we can multiply the power by the angle, or by the argument. So what we get is cos of 100 times 315. That's 31500, 31,500, plus I times the sine of 31500. So that step was de Moivre's theorem. Now that's not obvious by any means. We'll look at a proof of that later. So how could we simplify root 2 to the power of 100? Well, root 2 is 2 to the power of a half. And we want to put 2 to the power of a half to the power of 100. Well, 100 times a half is 50. We just multiply the powers. So we get 2 to the power of 50 out here. I won't write this down again. I'll just go to the calculator and work out, get this back into rectangular form. It's in polar form here. So to get the real part, we multiply 2 to the power of 50 by the cos of 31,500. Well, you can see that it's such a large number that I won't actually write it down. What I will do is I'll just write down the cos of 31,500 and the sine of 31,500 and leave this factor of 2 to the power of 50 outside. The cos of that angle is minus 1. The sine is 0. So we have a real number. We have 2 to the power of 50 times minus 1. Here is the statement of de Moivre's theorem. Cos theta plus I sine theta to the power of omega, or w, is cos w theta plus I sine w theta, where w is actually any complex number. Now we will prove this theorem for the case where w is an integer, or well, a positive integer, or any integer. Any integers, the set of all integers is denoted by the letter z, or any rational number, where a rational number is a fraction where both a and b are integers. So we'll prove it for all these situations here. I won't prove it for any complex number c, but it's actually true. W itself could be any complex number. So that includes all the real numbers, basically, because the real numbers is a subset of the complex numbers. First of all, we're going to look at a proof for when little n is a natural number. That means a positive integer. So I've replaced omega with the letter n, because usually small n is used to denote integers. Now, the set of natural numbers usually does not consist of 0, but I'm going to prove this for n equals 0 as well. So I'm going to start by proving that this is true for n equals 0. So let's look at the left hand side. What's the left hand side when n is 0? Well, we just get cos theta plus I sine theta to the power of 0. Anything to the power of 0 is 1, and we want the same rules to apply for complex numbers. A complex number raised to the power of 0 is also 1. Now let's look at the right hand side. So we replace n with 0. So we get cos of 0 times theta. Well, that's 0 plus sine of 0 times theta. Well, we know that the cos of 0 is 1. The sine of 0 is 0. So we get 1 plus I times 0, or just 1. You see, both sides are the same. So de Moivre's theorem is true for n equals 0. Now, let's see if it's true for n equals 1. This will be the first natural number, if we're assuming that the set of natural numbers begins with plus 1. So we look at the left hand side here, replace n with 1. So we get cos theta plus I sine theta all to the power of 1. What about the right hand side? We replace n with 1, so we get cos of 1 times theta. Well, that's just cos theta, plus I sine of 1 times theta, which is just theta. But of course, cos theta plus I sine theta to the power of 1 is just cos theta plus I sine theta. So we see that de Moivre's theorem is true for n equals 1. Now look at the case for n equals 2. So the left hand side is going to be cos theta plus I sine theta to the power of 2. Now, we can write that as cos theta plus I sine theta times cos theta plus I sine theta. We're just squaring it, we're multiplying it by itself. And then we can use the result of a previous video where we explained how to multiply two complex numbers together. We multiply the arguments of the two complex, the moduli of the two complex numbers together. So the modulus of cos theta plus I sine theta is just 1, or is 1. And the modulus of this one here is also 1, so it's like 1 times 1, which is 1. So that doesn't do anything in this case. We multiply the moduli, but the most important thing is we add the arguments. So when we multiply these two complex numbers together, we add the arguments. So we add theta onto theta. So we get theta plus theta. But of course, theta plus theta is 2 theta. And that's precisely equal to the right-hand side when n is equal to 2. We replace n with 2, we get cos 2 theta plus I sine 2 theta. So we see that de Moivre's theorem is true for n equals 2. Now, how do we keep on extrapolating? Let's look at n equals 3. Well, n equals 3 is, for the left-hand side, we get cos theta plus I sine theta to the power of 3. But we can factorize this into cos theta plus I sine theta squared times cos theta plus I sine theta. We already know that cos theta plus I sine theta all squared is cos 2 theta plus I sine 2 theta. And when we multiply by cos theta plus I sine theta, what do we get? Well, we can use the result of a previous video for multiplying complex numbers. We add the arguments. So what we get is cos of 2 theta plus theta, which is 3 theta, plus I sine of 2 theta plus theta. So we see that de Moivre's theorem is true for n equals 3. If we plug 3 into the right hand side, we get cos 3 theta plus I sine 3 theta. So we could keep going like that. What would we do for n equals 4? Well, we could write cos theta plus I sine theta to the power of 4 as cos theta plus I sine theta cubed, because we've already worked this out. We know what it is. It's equal to this. And we would have to multiply this by cos theta plus I sine theta to the power of 1, because 3 plus 1 is 4. So we know that this thing here is going to give us cos 3 theta plus I sine 3 theta. So when we multiply by cos theta plus I sine theta, we add the arguments. So we get cos of 3 theta plus theta, or cos of 4 theta. So that's how we could keep going. So you can see it's fairly obvious what's going to happen for n equals 5. Cos theta plus I sine theta to the power of 5 is just cos theta plus I sine theta to the power of 4, which is this here, multiplied by cos theta plus I sine theta. So we'd end up getting cos of 4 theta plus theta, or cos of 5 theta plus I sine of 5 theta. So now we know that if the theorem is true for any positive integer k, then the theorem is true for n equals k plus 1 if we add 1 onto that integer. So if it's true for n equals 2, it's also true for n equals 3. If it's true for n equals 3, it's true for n equals 4. If it's true for n equals 4, where k is 4, then it's going to be true for n equals 4 plus 1, or n equals 5, and so on. So what I've given is a kind of a proof by induction. It's not the usual proof by induction. It's not the usual proof by induction method that's given, so I'll give the more usual method of proving it, but the proof I just gave is perfectly adequate. Now, the more usual way of proving de Moivre's theorem for natural number n is to, first of all, see that it's true for n equals 1, which we've just done, and then assume true for n equals k. In other words, if we replace n with k, we're assuming that cos theta plus I sine theta to the power of k is equal to cos k theta plus I sine k theta. So this would be the second step in proof by induction. The first step would be to prove that the theorem is true for n equals 1. The second step is to assume that the theorem is true for n equals k, where k is any integer greater than or equal to 1. So we include the base case for k. So k could be equal to the base case, which is 1, n equals 1. The third step in proof by induction is to prove that the theorem is true for n equals k plus 1. So if we replace n with k plus 1, we get cos theta plus I sin theta to the power of k plus 1, and the right hand side becomes cos of k plus 1 times theta plus I sin k plus 1 times theta. So we want to prove that this is true by building on this statement here, which we're assuming to be true. So we're assuming that this statement is true here. This is from part 2. And we want to build on this. So in particular, we can multiply both sides of this by the same thing, and so on. And if we can end up getting this here, then we're done. So we start with this here. This is the statement that we're assuming to be true. And what we do is we multiply both sides of it by cos theta plus I sin theta. Now the reason that we do that is because if we multiply the left hand side by cos theta plus I sin theta, we will get the left hand side of the statement that we're trying to prove. So we multiply this here by cos theta plus I sin theta. So I'm just showing the multiplication on the left hand side now. But of course we just add the powers, so we get cos theta plus I sin theta to the power of k plus 1. So that's what we get when we multiply the left hand side by cos theta plus I sin theta. And what about the right hand side? Well, we have cos k theta plus I sin k of theta multiplied by cos theta plus I sin theta. So we have to do the same to both sides. So we're assuming that this is true. But if we multiply by this, you see that we do indeed get the left hand side of what we're trying to prove. We get cos theta plus I sin theta to the power of k plus 1. So you always build on what you're assuming to be true. So you can see now that the left hand sides, these are the same. So all we've got to do now is show that the right hand sides are the same. Show that this thing here is equal to this here. So let's multiply this out. We have cos k theta by cos theta. Okay, there's no I term in that. And what other products give us no I term? Well, if we multiply I sin k theta by I sin theta, we get I squared sin k theta sin theta. But I squared is minus 1. So I've just written out products that do not involve I. So if you multiply cos k theta by cos theta, we get this. And if we multiply I sin k theta by I sin theta, we get I squared sin k theta sin theta. But of course I squared is minus 1. So what we get is minus sin k theta sin theta. So those are the terms that do not involve I. Now we write down the terms that do involve I, but I'll factorize I out. If we multiply I sin k theta by cos theta, and if we multiply cos k theta by I sin theta, so there we have it. We have 4 terms, 1, 2, 3, 4, as expected, because there are 2 terms here and 2 terms here. So we end up with 4 terms. So that's the result of expanding this out. And we want to show that this here is equal to cos of k plus 1 times theta plus I sin of k plus 1 times theta. So this is where we use a trigonometric identity. We see that the real part of this expression, the real part is everything that does not involve I, has the form cos A, cos B minus sin A, sin B, where A is equal to k times theta and B is equal to theta. But cos A, cos B minus sin A, sin B is actually identical to cos of A plus B. You'll see this identity in tables. So that means that we can write this expression here as cos of k theta plus theta. So A is k theta, B is theta. Now let's look at the imaginary part. Now this expression here has the form sin A cos B plus cos A sin B, where A is equal to k theta and B is equal to theta. And this expression here is identical to sine of a plus b. A and b are any angles. So we can write down the imaginary part as sine of a plus b, where a is k theta and b is theta. But of course we can factorize theta out of this, so we get cos of k plus 1 times theta plus I sine of k plus 1 times theta, if we just factorize theta out of these terms. So that's exactly what we have to show. We have to show that this here is equal to this here. So what have we shown? We have shown that if the Moivre's theorem is true for n equals k, remember k is any number greater than or equal to 1, so it could equal 1, then the Moivre's theorem is true for n equals k plus 1. That's what we just showed. So in particular, if the Moivre's theorem is true for n equals 1, so if we let k equal 1, which we can do, then it is true for n equals 1 plus 1, which is 2. So now we've proven that the Moivre's theorem is true for n equals 2. So now k could equal 2. So if the Moivre's theorem is true for n equals 2, then it is true for n equals 2 plus 1. Here k plus 1 is 2 plus 1, which is 3. So now we've proven that the Moivre's theorem is true for n equals 3, and so on. We could replace k with 3, and since we know it's true for n equals 3, then it's going to be true for n equals 3 plus 1, which is 4. So now we've proven that the Moivre's theorem is true for n equals 4, and so on and so forth. So we can say now that the Moivre's theorem is true for all natural numbers.